Hi everyone, welcome to this session. We shall be looking at Kirchhoff's laws. In Kirchhoff's laws we have got two laws. The first one is current law and the second one is voltage law. So the first law, which talks about current, it states that at any junction in an electric circuit, the total current flowing towards that junction is equal to the total current flowing away from the junction. So basically, just like water, if you are having two streams flowing into a common point, the water draining into that point will be equal to the same water that will be leaving that point, irrespective of the number of channels it will use to exit that point. So it says the current draining into a common point will be equal to the current that will be leaving that particular point. So we can draw it like this. If you're having two branches, this is the first branch, this is our first branch, and we have our second branch this other side, like this. So if we say this is our first current and this is our second current that is flowing, and remember this is a common point, so the total of the two currents will be equal to the current that will be leaving this junction. Let's say this is another branch there, this is another branch here, this is another branch there. So let us say this is our I3, this is our I4, and this is our I5. So, and this is our junction. So Kirchhoff tells us that the sum of the two currents which are entering this junction will be equal to the current that will be leaving. Take it like water. This is the first channel, this is the second channel. The total volume of water flowing to this point will be equal to the total volume that will be leaving, irrespective of the number of channels the water will be using to exit this point. So mathematically we will say that I1 plus I2, this is the sum of the currents entering the junction, will be equal to the sum of the currents which are leaving the junction, which is I2, I3, I4 and I5, which is I3 plus I4 plus I5. So basically I've said if you sum up the two currents which are entering will be equal to the sum of the two currents which are leaving. It is very important whenever you are given such a question, you need to look at the directions, because the directions will guide you what is entering, what is leaving. So basically that is about Kirchhoff's current law. We are now moving to the second law of Kirchhoff's, which is about voltage. For voltage, it says the net voltage in the circuit is equal to the voltage drop around that loop. So we can read, in any closed circuit in a network, then the algebraic sum of the voltage drops taken around the loop is equal to the resultant EMF acting in that loop. That in any closed circuit, these are closed circuits, the algebraic sum of the voltage drops taken around the loop is equal to the resultant EMF acting in that loop. Basically we are saying the net voltage here, the net voltage in this circuit will be equal to the total voltage dropped by this resistor. From a layman's language we can say the voltage drop here plus the voltage drop here plus the voltage drop here will be equal to the net voltage in the circuit. Or rather you can say the net voltage in the circuit will be equal to the voltage taken by resistor 1 plus the voltage taken by resistor 2 plus the voltage taken by this other resistor. So mathematically we will say, because you can see this particular voltage source is draining this direction and this other one is taking current in the other direction. So what we will do, we will be able to take E1 as our reference. If you take E1 as our reference, it takes current in this direction. You can also see this other one is taking current in the other direction, meaning the two voltage sources are opposing one another. So what we do is you take E1 minus E2 because they are in opposition. So the net voltage is equal to E1 minus E2, that is the net voltage, will be equal to the voltage dropped by the total voltage dropped by the three resistors. The voltage dropped by this resistor will be equal to R2 plus the voltage drop here will be equal to R3 plus the voltage drop here will be equal to R1. Remember in my previous videos we said according to a series circuit, in a series circuit, current is the same, and that is why we are saying current across this resistor is I, across this resistor is also I, and across this other resistor will be the same current. So that is why we are saying E1 minus E2 will be equal to I R2 plus I R3 plus this one. So meaning this is the voltage drop. Voltage drop across R2. This is also the voltage drop across R3. This is also the voltage drop across R1. So basically we will say the total voltage drop across the components connected in that particular circuit will be equal to the net voltage in that particular circuit. So now that one takes us to we want to apply the two laws to be able to solve this example. We will take, we want to apply the two laws that we have learned to be able to solve this particular example. So the first thing we will do, we want to repeat drawing this diagram and indicate the direction. So the first step will be, we will draw this, the diagram as it is, and then we indicate our directions. Like this. This is the internal resistance of the cell. That is another voltage source there. We have another resistor there. So we have said this is our E1, which is 4 volts. This is our R1, which is equal to 2 ohms. Remember, this is our R, which is 4 ohms. This is the second source of EMF, which is 2 volts. This is R2, which is equal to 1 ohms. So in this particular case, we can take E1 as our reference. Remember, you can still take E2 as your reference. If you take E1 as your reference, it means then you have assigned the direction of the current to be this one. Let us say our I is equal to that, and we can call that is our I1 to be equal to that. Then the second thing we will do is to say that this second EMF will also be producing current in this direction. It will give us I2. Remember, current flows from the positive terminal of the cell. That is why I've said current is flowing from this direction. This other EMF is sending current in that direction. Remember, according to Kirchhoff's current law, there is a junction here. So I1 is draining into this junction, I2 is coming into this junction. All of them will be living through this junction. So we'll say the current flowing here is I1 plus I2. Very important. That the current that will be passing through this resistor is I1 plus I2. A very important step that you will analyze. After you have done that, after we have done that, we will now be able to generate two loops. We are having two branches here. We are having this one, we can call this one as loop 1. That is our loop 1. We can also say this is our loop 2. We can say that is our loop 2. Loop 2. After you have done that analysis, we want now to look at each loop independently. And I will redraw it again. I want to start with loop 1 and redraw it. In loop 1, you can see we having this. We have a resistor here. We have another resistor there. Like this. We have said what is here is I1. The current flowing across this resistor is I1 plus I2. Basically, this tells you that the current flowing here, the current flowing through this resistor is I1. Why am I saying it is I1? Because this resistor is an internal resistance of the cell. this cell is giving us I1. In fact, it's because we cannot be able to draw this resistor in this cell. We have to represent it outside here for purposes of clarity. But this resistor is within this particular cell. That is why we are saying this internal resistor experiences the same current I1. So our R1 experiences I1. But this resistor, remember this is 2 ohms, and this R, which is 4 ohms, it experiences I1 plus that. This is our loop 1. So after you have done that, we have applied Kirchhoff's current law to come up with this loop. The second step we will use Kirchhoff's voltage law. Kirchhoff's voltage law, which states that the net voltage in the circuit is equal to the voltage drop across the components. So that one will give us, this is our E1, which is equal to 4 volts. So it means E1 will be equal to the voltage drop here. We can start from this point. Is equal to the voltage drop across this resistor, which is I1, R1, plus the voltage drop here, which is R into I1 plus I2. Remember what I've said is the net voltage in the circuit, which is E1, will be equal to the voltage drop across this resistor plus the voltage drop across the other resistor. If you simplify this equation, you will get I1 R1 plus I1 R plus I2 R. If you so wish, you can be able to combine these currents, because at the end of the day we'll be working with currents. You can get it as I1 into R1 plus R plus I2 R. So that one forms our first equation. This one is going to form our first equation, but remember, we have the values and we can substitute. So that means our E1 will be equal to, what is our R1 and what is our this R? So it means R1 is 2 plus 4 plus I2 into 4. Remember, this one simplifies to 6I1. E1, we also know it is 4. We also know that equation simplifies to 4I2. So we can basically say that this one is our first equation. We have generated our first equation. After you have done this, we are now moving to loop 2. We can even draw it here. We can draw our loop 2 here. Loop 2. Let us just have it on this other side. Let us have loop 2. When you are drawing loop 2, you can have it in this format. We have our resistor there. We have this voltage source. Our E2, which is equal to 2 volts. We also have a resistor there, which is R2, which is 1 ohm. We have said this current flowing here is I1 plus I2. Remember, we had also indicated this is our I2 that is flowing in that direction. Remember, like I told you, this resistor, which is denoted by small r, it is the internal resistance of this cell. Meaning, in the real sense, this resistor is inside this particular cell. So it experiences I2 because the source is I2. So this one experiences current I2. So after we have applied Kirchhoff's current law, we now want to move to Kirchhoff's voltage law, where we will be having E2 will be equal to the voltage drop here plus the voltage drop on the other side, which will be given by I2 R2 plus, want to get this drop, remember this is 4 ohms, will be equal to R into I1 plus I2. We can simplify further and have it I2 R2 plus RI1 plus RI2 plus I R2. We can put like terms together. This will be the same as I2 R2 plus R I2 plus R I1. This will be the same as you factor out I2. You can factor out I2. You factor out I2, you will get I2 into R2 plus R I1. So we have factored out this particular I2. Remember, after you have done that, you can substitute now these values. You can substitute these values. You know R2 is 1, so that you have I2 into 1 plus 4 I1. And remember, we also know E2 is 2 volts. We can also replace that one. You can also replace that. So once you do this, you can simplify. 2 is equals to 5I2 plus 4I1. You can write it so that this I1 comes first. So 2 will be equal to 4I1 plus 5I2. That one happens to be our second equation. So we have generated two simultaneous equations. We have generated two simultaneous equations which we are going to solve using N2 methods. Which we shall be solving using N2 methods. We can now solve the two equations using either elimination or substitution. We can use elimination or substitution to be able to solve those two equations. So I can write my first equation was 4 equals to 6I plus 4I2. My second equation is 2 equals to 4I1 plus 5I2. If you want to use elimination says that you want to do away with one particular point. So you can, let us use substitution. Substitution will be easier because I can see one of these. My first equation was 4 equal to 6I plus 4I2. My second equation is 2, 4I1 plus 5I2. That is okay. So for us to be able to solve this one, let us use elimination method. I'm going to use elimination method. Elimination method, I want to interchange these two. You can interchange these two. If you interchange these two, you will get, this is 5 and 4. You interchange these two these two coefficients. This one gives you 20 is equal to 30I1 plus 20I2. You can use this is 8 is equals to 16I1 plus 20I2. If you subtract this, of course this one gives you 0. This one gives you 14I1 and this one gives you 12. This one gives you 12. So your I1 will be equal to, your I1 should be equal to 12 over 14. I1 will be equal to 12 over 14. Remember, this one can be simplified to 6 over 7 amperes. So you have now been able to get I1. We can now get I2. You can use any of these equations. You can use any of these equations. Like you pick I1, equation 1, which is 4 is equal to 6I1 plus 4I2. If you pick this second equation or first equation, you can replace I1. If you replace I1, you'll get 4 is equal to 6 into, if you replace I1, you'll be having 6 over 7 plus 4I2. So remember, this one will give you 4 is equal to 36 over 7 plus 4I2. So 4I2 will be equal to 4 minus 36 over 7. So I2 will be equal to 4 minus 36 over 7 divided by 4. If you do that math, your I2 will be equal to minus 2 over 7. Will be equal to minus 2 over 7 amperes. That is what you will get as your I2. Finally, because you want to get now your I3, or the current that is flowing across this resistor. We want to know the current that is flowing across this resistor. We say the current flowing in this branch. Remember, I1 is the current flowing in this branch. I2 is the current flowing in this branch. So we want to get the current flowing in this branch. What do? We say the current flowing in this branch is I1 plus I3 plus I2. So that means the current flowing across R will be equal to I1 plus I2. Our I1 is here, will be equal to 6 over 7 plus I2. Our I2 is here, so plus minus 2 over 7. Remember, plus and a minus is the same as a minus, so this one should give you 4 over 7 amperes. So the currents flowing in these branches are, the first branch is 6 over 7, the second branch is 4 over 7, this one is equal to minus 2 over 7. These are minus because it is going against this other source. So that is the end of this particular question. It's a very common question in a NEC papers, and make sure you get all these steps right. So with that, we can stop there.